Hello and welcome back. We'll look at some problems on thermodynamic cycles. So, we'll go on first to the Rankine cycle, which we have discussed earlier. So, this problem says there is a steam power plant which is operating on the Rankine cycle. Steam enters the turbine at 4 megapascals and 400 degrees centigrade and exits at a pressure of 15 kilopascal. Then it enters the condenser and exits as saturated water. Then a pump feeds back the water to the boiler. The adiabatic efficiency of the turbine is 90%. What is meant is essentially the isentropic efficiency is 90%. We are asked to determine the heat supply to the working fluid in the cycle and the net work output of the cycle. So, let us try to draw a schematic of the working cycle on a TS diagram. So, this is a Rankine cycle. This works on two-phase flow. So, let me draw the liquid vapor dome. The working substance in a Rankine cycle is water or steam in the usual Rankine cycle. So, it says steam enters the turbine at 4 megapascal and 400 degrees centigrade. So, at the turbine inlet, I have steam at 4 megapascal, 400 degrees centigrade. I do not know where this point is. I need to find out where this point is by using the steam tables. What I know is at this turbine exit, the pressure is 15 kilopascal. That is something else I know. In the ideal Rankine cycle, this would be an isentropic process. So, I should be able to draw this. But in this case, I am also given an adiabatic efficiency for the turbine or an isentropic efficiency for the turbine, which is 0.9. So, what I can do is first draw the ideal cycle and then draw this real cycle. What we know is it enters the condenser and exits as saturated water. So, at condenser exit, I have saturated water, saturated liquid, and then I have a pump which feeds it back to the boiler. Okay. So, let us find out where this condition is. We want to see where we have 4 megapascals and 400 degrees centigrade from the steam tables. I have here the steam tables. We are looking for 4 megapascals. So, we will go on to the pressure table. So, I have 4 megapascals here. The saturation temperature is 250 degrees centigrade at 4 megapascals. So, I have a temperature of 400 degrees centigrade, which is much higher than this. So, therefore, it must be in the superheated region. So, that information is sufficient for me for the moment, so that I can draw it. So, what I know is my initial point is somewhere here. Let us say somewhere here. So, if I was to draw this process, I would have something like this. So, I have some point, this is the condenser outlet, this is essentially the pump. So, let me call this condenser outlet, which is the pump inlet, as some 1. Point 2 is the inlet to the boiler. From 2 to 3 to some 4 to some 5 is heat addition in the boiler. From 5, the ideal process would have essentially an isentropic process. I do not know where this will end, whether it ends inside the dome or outside the dome. I need to find that out from the entropy values, and later on I will have a horizontal process here, either completely horizontal or partially on the constant pressure line, depending on where this thing ends. So, I know that 5 is superheated. So, let me find out for the ideal process what happens first. So, for the ideal process, my point 5 is 4 megapascal 400 degrees centigrade. I can find out the enthalpy, I can also find out the entropy. These should be there in the superheated tables. So, that is essentially what I am going to do. So, I am going to look at the superheated tables again. So, I have here the superheated tables. Of course, this goes on only to 2 megapascals. So, I need the next page. So, 4 megapascals is here. I need 400 degrees centigrade, which is essentially these values. So, the enthalpy here is 3214.5 and the entropy is 6.771. So, these are the values I have. So, I need to find out where this end point is from 5. So, let me just draw some kind of a schematic. This would be the constant pressure line going through 1. This will go something like this. I know the entropy over here. In the ideal process, the entropy at the end of this process should be the same as the entropy here. So, what I am going to do is, I am going to find out the entropy on this constant pressure line. This is 15 kilopascal, this is 4 megapascal. I am going to find out the entropy on the vapor line on the 15 kilopascal line and then compare it with the entropy on this line going down from 5. If the entropy here is lower than the entropy at 5, then it means that this line comes to the right. If the entropy is the same, then this line passes through this point. If the entropy here is less, it means that this line comes down to the left. So, I do not know where it comes. So, I am going to find that out by looking at the entropy of the vapor phase, the saturated vapor at 15 kilopascals. So, let me look at that again. So, I need the values at 15 kilopascals, which is 0.015 megapascals, which lies between these two. So, the entropy over here, I am interested in these values. So, the values here are 8.0311 and 7.9846. So, I am going to take the average of those two, because I want the values at 0.015 kilopascal. This gives me a value of 8.007. So, what we see is that the value of Sg at 15 kilopascal. So, Sg at 15 kilopascal is essentially this point. At this point, the entropy is 8. This is a TS diagram. Here, the value is 8. And in my isentrope from 4 megapascal and 400 degrees centigrade, the value is 6. So, which means when I reach this point here, my isentropic line will lie somewhere here, because it is less than 8. So, now I know how to draw my cycle. So, it is something like this. It starts somewhere there. This is of course line parallel to the t axis, but it ends to the left of this point. So, this is this line corresponds to 4 megapascals. This is a constant pressure line corresponding to 15 kilopascal. So, 1 to 2 is isentropic parallel to the t axis. From 2 to 3 to some 4 to some 5 is constant pressure. 5 to 6 would be the isentropic line parallel again to the t axis. So, this 1, 2 and 5, 6 are parallel lines. 6 to 1 is parallel to the s axis. So, this is what the ideal cycle would look like. So, for this ideal cycle I can find out various properties and find out what we need to find. So, we are asked to find out the heat supplied to the working fluid in the cycle and the net work output of the cycle. So, the heat supplied is supplied here in this process 2, 3, 4, 5, the constant pressure process. So, I need to know how much the heat supplied is. So, from the first law for this process, we have this. This is generally expected to be steady state. So, this is 0. There is no work done in the heat exchanger. This is 0. Changes in potential and kinetic energy are usually negligible, and I do not know anything about the velocities. So, I will assume that this is 0, which then gives me Q. If I from the first law, from the conservation of mass, I also have this, and this is steady state. This is 0. Mi dot is equal to me dot is equal to some me. So, some m dot, and then I can divide q dot by m dot and get q. So, I get q is essentially enthalpy at the exit minus enthalpy at the inlet. So, the enthalpy at the exit is enthalpy at this point. I have already found out that. I need the enthalpy at the inlet, which is the enthalpy at this point. I need to find out that. So, what I need to find out now is H5 is this over here. I need to find out H2. Let me just confirm I have been using the same nomenclature in both the figures. Yeah. So, I need to find out now H2. How do I find H2? So, I know at point 1 I am at saturated liquid. At point 2 I know the entropy is the same as the entropy at point 1, and I know the pressure on this line 2, 3, 4, 5. So, geometrically if I look at it, if I draw a vertical line through 1, wherever it intersects this line, that is essentially where my point 2 lies. So, if I can do it geometrically, I should be also able to find out the values. So, the concept here is that at 1 and 2 entropy is the same. So, let me find out what is the entropy at 1. So, at 1 I am on the 15 kilopascal line on the saturated liquid intersection point. So, I am looking at the intersection of this dome with this 15 kilopascal line. So, essentially this is S1 is equal to SF at 15 kilopascal line. That is, I can find out this value. S2 is equal to S1, which is the same value as this. The point 2 is a point on the 4 megapascal line, which has the same entropy as point 1. So, that is one way of finding it. Other way of finding it is that I know at point 1 what the enthalpy is. I know that I am doing work in 1 to 2. So, if I add the amount of work I do to the enthalpy at 1, I can find out the enthalpy at 2. So, any of these ways I can try to find it. So, first let me find out what is the entropy and enthalpy at point 1. So, let me go back to the tables. We are again here. So, I want the liquid enthalpy, which is essentially these two. So, I have 220 and 231.6. So, the average of that would essentially be 225.8, which is the enthalpy. Then I have the entropy, which I had already found out somewhere, which is essentially 8.007. I found out SG not SF. Okay, so I need to find this out again. I need essentially these values. Okay, so I have 7366. Am I looking at the right one? Yes. So that's 0.7543. So, in many of the tables, what we would see is that we are also given liquid tables for this region. So, in the tables which I have been referring to, we have initially saturated liquid properties, liquid and vapor properties, which means we have the properties given on this dome, on the left and right of this dome, and then we have superheated properties which give essentially properties in the superheated region. In the same fashion, we can also look at properties of saturated liquid, which would give you properties of stuff in this region over here. So, if I was to look at those tables, and in those tables, if I was to see what is the point, what is the temperature at which the entropy is this and the pressure is this, I should be able to find out that point and correspondingly find out its enthalpy. So, if I had those tables, that is the way I would do, which is why I wrote these entropy values. I would look in those tables for a case where I know that the pressure is listed as 15 kilopascals, and I will see at which temperature the entropy comes out to be this value, and that would be the point. But right now I do not have those tables with me. So, what I am instead going to do is find out the enthalpy at 1. I can find out how much work I do in going from 1 to 2, and then add this work and then find out the enthalpy at 2. So, the reason I can do that is if I look at the pump work, which is WP, I know from the first law again that this is true. There is only one inlet and one outlet, it is steady state. So, I am using this again and just writing this. Enthalpy at the exit, kinetic energy, potential energy exit, and so on. It is a steady process, this is 0. This is 1 to 2 is an isentropic process, which means it is adiabatic and reversible. So, this is 0. Changes in potential and kinetic energy are typically small. I am going to neglect the change. So, that is 0, which then tells me that W dot is m dot into this, or essentially small w is this. So, what I want is the enthalpy at the exit, which is essentially HE or H2. So, that is essentially, so over here of course W would be negative, okay. So, this value would turn out to be negative. So, if I was to find out this thing, this would say that this is enthalpy at 1 minus of W. W itself would be negative. So, this would be H1 minus some negative quantity which would be positive, or more simply I can write it as H1 plus mod of W. I have some enthalpy at the inlet. I am doing some work on this fluid and increasing its enthalpy further. So, I should add it in order to get the enthalpy at the exit. So, the enthalpy at the inlet I have here, I need to find out the work. So, we again discussed just a little while ago also that TdS is dH minus VdP. Since the pump is considered as isentropic, this is ds is 0, which tells me that dH is equal to VdP. So, we can use this expression. V, we are assuming it to be constant, we are assuming this is an incompressible fluid. So, we can find out what the value of V is from the tables. This is a specific volume of liquid at 15 kilopascal, because we are given that the entry is liquid at 15 kilopascal. So, let us find out that. So, I have 0.001013, 0.001015. So, the average of these two, I am looking for 0.015 kilopascal, which is in between these two. So, the average is 0.001014. That is a specific volume. So, what I am saying is delta H is integral of this. I am taking V as constant and just integrating dP. dP is final pressure minus initial pressure, which for me is 4 megapascals minus 15 kilopascal. So, these are in pascals, this is in meter cube per kg. I will get an answer in joule per kg. What I will do is I will convert it back into kilojoule per kg, because my other values are in kilojoules per kg. I believe this value comes out to be about 4.04 kilojoule per kg. So, my W is essentially mod of W is H2 minus H1, which is this. So, H2 is H1 plus a delta H, H1 is 225.8. So, we have found out this. The reason we were finding out this is because we wanted Q, which is essentially Hg minus this thing, which is essentially H5 minus H2. H5 is here 3214.5. which gives us a value of about 2984.66 kilojoule per kg, which is the amount of heat which is transferred. So, we have found out the amount of heat transferred. We are asked to find out the net work output of the cycle. So, the net work output is essentially the work done in this process from 5, minus whatever work we are doing in the minus the positive work done in process 1 to 2. So, that is what we want to find. Okay. So, that is something we need to find out now. So, we know the pump work, which is essentially this value. We have that. We need to find out the work during the expansion process. Now, if this was an ideal process, we would go from 5 to this 0.6. So, we can find out what would be the work in the ideal process. For the ideal process, we know the inlet condition, which is enthalpy at 5, we know the entropy at 5. For the ideal process, this 0.6 lies on this 15 kilopascal line. It has the same entropy as the initial. So, we can use that information to find out what is the quality at 0.6. So, if I was to write for ideal process, five to 6, so S5 should be equal to S6. Now, S5 we know the value already, that is equal to something. Now, S6 I can write in terms of SF plus X into SFG, and then find out X. SF and SFG are at 15 kilopascal. So, I need to find out all of these. So, S5 we just noted here is 6.771. SF we do not have yet. Oh yeah, SF is essentially 0.7543. And SFG we need to find out from the tables. So, we are going to look at the table for 15 kilopascal. SFG is the average of these two. Which gives me a quality of this. Knowing this quality, I can find out what would be the enthalpy at 0.6. I think HF at, I already have here 225.8. I need HFG value. I need to look at the tables again. HFG is essentially average of these two values. Which gives me this. So, in the ideal process, the work done is the difference between the enthalpy at the inlet and the enthalpy at the outlet. Enthalpy at the inlet is H5 is 3214.5. And at the outlet is essentially what I just found out, 2192.5. which is 1022 kilojoule per kg. So, this would be the work I would have got if this process was isentropic. What we are given here in the question is that the adiabatic efficiency of the turbine is 90%, which means that instead of getting a process like this, I get some process which is something like this. I have not found out where exactly this last point is. I do not necessarily need it for this question, but I can find out. So, but right now I am not going to do that, but I will need to find out how much is the work. So, if I call this SM6 prime, the isentropic efficiency is defined as H5 minus H6, sorry, H5 minus H6 prime divided by H5 minus H6. So, what I am given is that this is 90%. This is essentially the work which I really get by the work which I would have got if this process was isentropic. So, I know this value and I know this value. So, what I want to know is this value, this actually work actual divided by WT ideal. So, this tells me that the actual work which I get is this value which I got into 0.9 which is essentially what we are asked to find out. So, in this question what we saw is that we initially had information about this point, we had information about this point which we found out from the tables, it is superheated. We did not know where this ends. So, we compared the entropy values on this line with respect to the entropy here and then found that this is actually to the left, and so we drew it like this 5 to 6. We knew all the values here, we did not know the enthalpy here. We took the enthalpy here, added on the amount of work done and then got the enthalpy here. The heat addition is the enthalpy at 5 minus the enthalpy at 2. The work done is enthalpy at 5 minus enthalpy at 6. In order to find 0.6, we used the concept that the ideal process 5 to 6 is isentropic, which gave us the entropy at 6, and we were able to find quality at 6 and use it to find out enthalpy. And then we used the adiabatic or isentropic efficiency, which tells us that the efficiency is whatever is the real work we get divided by the ideal work which we would have got. So, using that we were able to find out the amount of work we can get from this non-ideal process as well. So, thank you, and we will go on to the next topic in a little.